All right. So the major gap we would like to address through this work is first that most previous works who have worked on simulators, they have mostly worked for a single agent for autonomous racing, like the TORCS simulator. One of the ones which have used for head-to-head racing is this previous work, but it uses on a modified go-kart Unity environment, which is based on a kinematic model of the vehicle. So in this work specifically, we propose a more accurate simulator for head-to-head autonomous racing. Also, most of the works, even on a single agent, have not been able to achieve optimal policy with using reinforcement learning for the controller. So in this work, we're also proposing curriculum-based reinforcement learning in order to achieve more optimal policy. So the brief overview of this work is that we'll first propose a reinforcement learning based controller, which has a hierarchical control design, where we would have a high-level planner which would output a strategy in terms of the waypoints, which would be followed upon by the low-level controller, which will be trained by RL. For the high-level tactical planner, we first discretize the state as follows, where we discretize the position into a checkpoint and the lane ID format, where we divide the track into discrete lanes, and the output from this high-level planner is a series of waypoints of these discrete states, and the optimal high-level plan is obtained by Monte Carlo tree search, where the opponent agent is assumed to be adversarial. So the way it proceeds, an example of this is for each high-level state, we determine if the vehicle can transition to the next set of waypoints onto the next section, and based on that decision, we alternate between the ego agent and the opponent agent, where we assume that the opponent agent will also perform adversarially or optimally, and give out its section so as to minimize the time difference with respect to the ego agent. And based on that, we roll out a fixed sequence of actions, and the best one where the ego agent thinks it can achieve maximum time advantage with respect to its opponent is chosen. Then we have the low-level controller, which is tasked to track the waypoints obtained from this high-level plan. And the low-level controller is trained using the RL proxy policy optimization algorithm using Unity ML agents framework. We train it on all kinds of tracks with anti-clockwise and clockwise directions with all different sizes, so that it doesn't overfit on a fixed track shape. The observations consist of the inertial state of the vehicle and the opponent if it's present within a specified range, the lidar raycast distances, as well as the target waypoints from the high-level tactical planner. Rewards are chosen so as to, for the low-level controller, so as to make the agent adhere to the plan obtained from the high-level planner as closely as possible. It is rewarded for going through the checkpoints which are planned and crossing the most number of as many checkpoints as possible, and it is penalized for serving too frequently or colliding with the opponent. Our next contribution is introducing curricula in the reinforcement learning framework. The way curriculum-based RL works is that if you would have a notion of an easier to solve environmental setting, and then if we could make it progressively difficult. This is analogous to how humans learn as well, where we would have taken like a class course where we first learn the easy stuff and then build upon it to get to more complex tasks. This can be achieved by, let's say, for example, on the right, where if the goal is to reach a certain goal, the agent can start from closer to the goal, and once it has mastered to get to the goal, we can drift it away from the goal. Or it could also be achieved by using some sort of privileged information if it's possible, And if the agent is able to use that privileged information optimally, we could drop it gradually. For this work, we introduce curriculum in our RL framework where we gradually modify the vehicle model from the kinematic to the dynamic model. So to give a little bit of context, the kinematic model of the vehicle assumes that there is no tire slip. So things like drifting, like drifting is not accurately modeled. While with the dynamic model, we use a tire curve, which gives which uses force-based model, which more accurately models the drifting and skidding of the vehicle. The way we introduce curricula in our framework is that we modify the tire curve from a more steep curve to this less steep version, where the idea is that with a more steep curve, it would cause less drifting, which makes it easier for the RL agent to learn at the beginning quickly, and then would gradually descend towards the actual tire curve. So this way, the agent can learn to perform better at an easier environment at the beginning, and then move to a more realistic setting. Here is an example race between if with and without curriculum learning are used. So the one on the blue is the one where the curriculum learning is used. As you can see, it's able to kind of learn to move towards the checkpoints and make an optimal policy, but still it collides much with the track, causes a lot of track boundary violations. So towards this, we use control barrier functions, abbreviated as CBFs. I omitted a lot of math here in the interest of time. So based on this, we can design the following CBF to avoid track boundary violations. The basic idea behind using CBF on top of the RL policy is that while learning, we can override the command from the RL controller if it's about to cause any track boundary violation. And the amount of override that is caused by the CBF controller is dictated by these parameters lambda1 and lambda2. So the idea is that, for example, if we have, let's say, this set of commands by the plot on the left, where the red region is where the commands where the which do not satisfy the CBF, and if the RL commands from within the red region, the CBF controller finds the closest point on the green region, which would satisfy the CBF constraints and cause it not to have any constraint violations. So higher value of lambda would cause a larger red region, which would cause more interference from the CBF controller. So we would change the CBF parameters from a higher value of lambda all the way up to 0 to signify that for a higher value, it would assist the RL policy more in moving towards the safe policy at the beginning, and then would gradually change it to no interference with the RL policy, so it can learn to avoid constraints by itself. Here are the comparisons and the rewards obtained by if we use both model and CBF-based curricula, while versus if we only use model-based curriculum, or if we do not use any of them. And as you can see, with using both kinds of curricula, we are able to achieve higher rewards in here. Here is an example race. I'll quickly just only play one of them in the interest of time. So the blue agent is the one where where both CBF as well as model curricula has been used for training, and yeah, it would be able to eventually overtake the other agent, and yeah, move safely. So yeah, so then we conduct races among these five different algorithms with which we train the agent. We conduct 20 races among each pair of them, and just to see how it performs. We also use the classical LQR controller to track the MCTS waypoints. to see how well the RL agent performs against a classical controller. And we also use an end-to-end agent where we do not have the hierarchical framework to see how it compares against it. And we are able to win most of the races with all of these. Yeah, some more results. And yeah, the future plan, however, is to also test the CBF-based curricula on other prominent mobility-based environments like the safety gym environment suit and the Carla RL environments. Here are some preliminary results which I have on the safety gym environment, where I modify the CBF parameters in a similar fashion. And it's able to beat the PPO Lagrangian, which is a variant of PPO to be used with constrained in a constrained setting. But yeah, more results will follow on this. Yeah, so that's it from my side. And yeah, if any questions or any suggestions are welcome. Thank you.
So it's a really good work, and you are coding safety constraints manually into your RL controller to get better performance. But this involves a lot of engineering. Do you think involving some kind of demonstrations to learn some constraints from demonstrations might be a good future direction of work?
Yes, I think so. Also, there are some works which learn CBF model, which also learns models as well as CBF from the data. So I think it's an interesting direction to explore to learn CBF along the way and not to engineer it for each new environment. And yeah, I think there are some couple of recent works on that.
Thank you very much. And for our next talk, we'll have Tanmay and Samak on multi-agent deep reinforcement learning for cooperative and competitive autonomous vehicles using the AutoDRIVE system.
To be on this record as well. Very good evening, everyone. Thank you for joining our talk on multi-agent deep reinforcement learning for competitive and cooperative autonomous vehicles using AutoDRIVE ecosystem. So let us start a little bit about the research motivation. So reinforcement learning, as we all might be aware of, is the concept of learning through experience. But the challenge becomes quite difficult when we move from just reinforcement learning to multi-agent reinforcement learning, wherein the scenarios are now highly complex and dynamic. There is a lot of stochasticity involved in the scenario. And even in multi-agent reinforcement learning, the overall objective of these agents could be either competitive or cooperative or both of them simultaneously. So in the context of autonomous vehicles, cooperation could be something like traversing an intersection safely, which is predominantly utilized in the autonomous driving or intelligent transportation systems. Or it could be competitive, such as head-to-head autonomous racing, as shown there. And there could be also a possibility of having competition and cooperation simultaneously. For example, if we consider a head-to-head autonomous racing event, although the overall objective is to compete against each other, these agents should also cooperate with each other to ensure that there is no collision between the two agents. We leveraged what we developed and what we call AutoDRIVE ecosystem to model and implement this multi-agent reinforcement learning framework. So just to give you or introduce you to AutoDRIVE, it basically is comprises of a dev kit, that is a collection of flexible APIs and tools to develop autonomous driving as well as smart city applications. We have a high fidelity simulation system that can be used for virtual prototyping, digital twin applications for basically using variability analysis and doing rigorous verification and validation of your autonomy algorithm at an earlier stage. And finally, a hardware test bed for physical or hybrid validation of the problem at hand. So let us talk a little bit about the creation of the digital twin models for the reinforcement learning task. we have modeled two different vehicles. One is Nigel, which is the native vehicle of AutoDRIVE ecosystem that we started off with, which is a 1:14 scale Ackermann steered vehicle. It's basically targeted towards autonomous driving and intelligent transportation using V2X communication and things like that. And recently, what we have done is we have also brought in the F110 vehicle, which is a 1:10 scale vehicle targeted towards autonomous racing operational design domain. And we have now set up these both and other vehicles, full scale vehicles, in a digital twinning framework with respect to giving good amount of thought on the dynamics as well as perception interfaces for ensuring higher simulation fidelity. To talk about dynamics interface, the vehicle are represented as a combination of sprung and rigid body representations. And at these two interfaces are connected using the mass, moment of inertia, and center of mass parameters. We have modeled the suspension dynamics as mass spring damper systems, and the tire dynamics are modeled as two-piece splines to ensure lateral as well as longitudinal slip profile correlation with respect to the tire forces. And these together in combination with the actuator dynamics that also include the saturation limits as well as the dead bands of each of these actuators ensure proper Ackermann steer vehicle dynamics for both yaw plane dynamics as well as vertical dynamics. For the perception, we have throttle and steering feedbacks that are actually measured from the dynamically simulated throttle and steering actuators. In addition to that, we have indoor positioning system and inertial measurement units that utilize the temporally coherent data of rigid body transforms of the vehicle with respect to the world frame or inertial frame of reference to update the position, orientation, linear velocity, angular velocity, as well as the accelerations. And we also have modeled the incremental encoders based on the drive actuators, the wheel radius, as well as the deformation that happens on the tires, as well as the resolution of these encoders. We have LiDAR that uses active raycasting methodology to ensure the range, the linear and angular range, as well as the resolution and update rate of the LiDAR is matched with respect to its physical counterpart. And for cameras, we use viewport rendering pipeline, which basically utilizes the rigid body transformation of the camera frame with respect to world and a perspective projection matrix to utilize parameters such as the focal length, the aspect ratio of the sensor, as well as the sensor offsets across each dimension to render the camera images. And in addition to that baseline we also have post-processing scripts that take care of other nonlinear effects such as distortion or chromatic aberration or ambient occlusion and things like that. So let us now talk a little bit about the two different case studies that we have implemented using this ecosystem. So the first case study is that of a cooperative scenario where we use the application as an intersection traversal. And the problem formulation for this is based upon a partially observable Markov decision processes where each of the agents is only aware of limited states of its peers, and there is no active perception involved directly. So the observation space here consists of the relative goal of each agent with respect to itself, the relative peer poses, as well as the absolute peer velocities, which are now communicated using a V2V communication framework and estimated using the encoders on the wheels. In terms of action spaces, the vehicle throttle is capped at 80%, and the agent is now choosing discrete action commands for steering the vehicle in either of the directions, as well as moving state if required. And we formulated the reward, of course, to now give award after crossing the intersection safely. But instead of just giving a constant penalty upon collision, we are now also adding a gain, which is the distance from the goal that the agent collided. And the ideology behind that formulation was to push the agent towards the goal, no matter if it didn't reach the goal initially, and basically guide it towards the goal. And here we are using a pure reinforcement learning framework to now update the policies. And we have two different scenarios, a single agent learning scenario wherein only one agent is learning, and then we transition towards a multi-agent learning scenario where all the agents were learning simultaneously to cross the intersection. So
We parallelize the training here in this case using multiple environments. And here, as you can see in this video, we have 25 parallel environments running 4 agents each, which totally comprises of 100 agents learning in parallel the same task of intersection traversal. And we analyze the training in terms of the cumulative reward that the agents are accumulating over the episode length itself, as well as the policy entropy. And here in the first column, we have the results for the single agent learning scenario. And in the second column, we have the results for multi-agent learning scenario. And although the profiles of both the columns look the same, the primary reason for the difference or high deviation in the second case is because of the higher stochasticity of the environments where all the agents were learning to cross the intersection simultaneously. Of course, at the end, we were able to train the agents to traverse the intersection safely. In the single agent learning scenario, it is interesting that depending on the velocities of its peers, the ego agent, which is now traversing from the bottom to the top, actually learned to choose either the left or the right lane of the other end of the intersection to mitigate or avoid the collision that would happen with the agent that's primarily coming from the right or the left side. And in the multi-agent learning scenario, similarly, you can see that all the agents have now learned after the training to traverse the intersection safely, like without colliding with each other or overstepping any of the lane bounds. So I'll now talk about the competitive case study, which is of autonomous racing. So here again, we formulated the problem as a POMDP with no state sharing this time, because being a competitive scenario, the agents were not allowed to share any of the state informations with each other. The only observations that each of the agents could have was its own velocity, as well as sparse LiDAR scan of 27 points 10 degrees apart as the physical F1 vehicle. And in terms of the action space here, the agents were allowed to control both the throttle as well as the steering of the vehicle in order to drive or race. And here, instead of formulating it as a naive RL problem, we formulated it as a guided RL problem with demonstrations to guide the RL agent in 2 different ways. One is using behavioral cloning, which was weighed equally as the RL updates. And secondarily, using GALE or generative adversarial imitation learning reward, which basically asks the RL agent to be as close to the demonstrations as possible while also maximizing other sets of rewards. And these other sets of rewards comprised of a curiosity reward, which guided the agent to explore initially and basically promoting different action outcomes for the same observations. And it was decayed exponentially as the training episodes progressed to now promote exploitation towards the other half of the training. And apart from this, we also had an extrinsic reward formulation, as mentioned towards the bottom of the central column, where the agents were, of course, penalized upon collision, but they were guided through different checkpoints, which gave them smaller rewards and higher reward towards the lap completion. And if the agent could possibly overcome its own lap time or beat the other agent's lap time, it was rewarded significantly. And otherwise, we awarded the agent proportional to its velocity to now come up with a reward formulation which maximized the velocity and minimized the time of lap completion. So here we trained only for multi-agent learning scenario, because that was kind of, depending on the application, that was the whole crux of it. And here we parallelize the training in a different way, where you have a single environment, meaning the racetrack, but there are multiple agents being trained parallelly in the same environment. And if you see, only the agents of a single family, which means 2 agents at a time, are able to collide, observe, or interact with each other in any form. So if you look closely, the LiDAR raycasts that the ego vehicle is currently visualized for is only hitting either the track bounds or its true competitor and none of the other agents that are learning in parallel. And similarly, if you see in the heads-up display, the camera preview of the ego agent is being visualized, where it only sees its true competitor and none of the other agents that are learning in parallel. Again, we analyze this training in terms of the behavioral cloning loss, which exponentially reduced over time. GALE reward, which for one of the agents started off pretty well, which means that it was primarily acting more towards the demonstrations provided, but then reduced, which means that it learned to explore and settle at a different behavior, and as well as curiosity reward, which both of the agents have maximized, and the episode length as well as the policy entropy, which has been converged, meaning the agents are most certain with their action based on a particular observation. So apart from completing several laps, the agents also did some interesting maneuvers or strategies to overtake each other. And here are just two sample use cases or 2 points in the deployment phase where we observed really cool overtaking strategies. So for example, in the first video on the left side, you have a block overtake strategy where the red agent keeps blocking the blue agent throughout the straight, but because it's on the inner side of the track, it compromises the turn and has to slow down there, where the blue agent quickly overtakes it and gains a leading position. On the right, you have a more interesting maneuver where the red agent now, because it knows that it would compromise the lap if it would go through the shorter curve, it goes wide, lets the blue agent overtake it, and because the blue agent now comes closer to the boundary of the racetrack, it slows down, and then the red agent finds the gap and just overtakes it right there and gains the leading position again. So thank you very much for your attention, and here are a few resources that will take you to the AutoDRIVE ecosystem, open source resources in general, and we would be happy to answer any questions at this point. Yeah, so right, so if you see the agent potentially could go straight only if it thinks that the other like peer agents, which are in the first case trained using heuristics, are not going to collide with it. But in the second scenario, since all the agents are now trying to parallelly traverse the intersection, you can clearly see, as you mentioned, the second point, where the agents are choosing the opposite side of the intersection, the lane in which they want to go, based on the states that the peer agents are now communicating with them.
Thank you very much. And then next we'll have Keiko Nagami from Stanford on learned objectives for game-theoretic planning.
Okay, hi, my name is Keiko Nagami, and today I will be talking about some work about learned objectives for game-theoretic planning. This work is in collaboration with Jaden Clark and Professor Max Schwager. Okay. So to motivate this problem, we want to consider sort of real world scenarios where you might find your autonomous agent interacting with other agents in your system whose objectives you may not know, and you are not directly communicating with these other agents. So the question we seek to try to address is, how can we approximate the objectives of these other agents in our system to be able to inform our own plans? So the approach that we take, we call learned trajectory tracking, or LTT for short. We divide it into 2 different sort of modules. So the first stage is an offline stage. So we assume that we have some data set that we can train a neural network to. So we use a variant of imitation learning known as Dagger to map a current joint state of all the players in the game to a predicted trajectory of some finite horizon. So then once we train that neural network online, we then query that neural network to generate a trajectory that's predicted by the neural network. And instead of just using that output, we then formulate a trajectory tracking cost. And we use this as an objective that we define for the other players in the system to input into a game theoretic solver. So to go a little bit more into detail on the offline stage, where we first train a trajectory predictor, as I mentioned, we assume that we have a data set of these trajectories of interactions with the players in the game. We then train the neural network that maps from the current joint state to a predicted trajectory. The reason that we choose not to directly use the output of this neural network is because it's difficult to satisfy dynamic constraints and collision avoidance constraints on these neural network outputs. So then online, we use a game solver to sort of correct these trajectories. So we formulate a objective function for each of the players as a quadratic tracking cost using the predicted trajectory from the output of the neural network. So in this optimization problem, namely the predicted trajectory that comes from the neural network is used in these terms here. And now we have a nice like quadratic tracking cost. And in our approach, we use AL games to then solve for a Nash equilibrium to this game. And yeah. Okay. So then as a full system, this is sort of how we're applying everything. So at time step K, we get the joint state of all of the players in the game. We then query the neural network at that joint state. We get a predicted trajectory to some like fixed horizon length. We then construct that trajectory tracking cost that I mentioned earlier. We use AL games to solve for a Nash equilibrium. We use that first control action for the ego agent, and then allow the system dynamics to propagate and sort of repeat this process in a MPC style fashion. So some simulation experiments, we've tested this on a double integrator dynamics model where we have 3 agents sort of planning along a track. So to generate the data for this simulation experiment, we ran AL games forward with a quadratic objective function to some desired goal state. And yeah, in this case, we use a longer horizon length of 20 in our data collection stage. Okay. So then we train our model on this data to a predicted horizon length of 5. And then we compare applying our method to just running the game solver to a horizon length of 5. And we find that our method is able to make further progress along the track faster. And we think this is because our method is trained on long horizon information, as opposed to the game solver that is only using the short horizon information. And then secondly, we also compared our method to the case where the game theoretic solver is solving at the full horizon length of 20. And we find that our method is able to closely match the performance of that ground truth, even when we're only planning with a horizon length of 5. In our next steps, we would like to apply this method to real racing data or data generated from agents with non-quadratic objectives, because in this simulated experiment, all of the underlying objectives were quadratic. And then another interesting future direction, I think, could be to use like a history of the states of the agents in the system as a way to sort of capture maybe like changing behaviors in opponents. That's all I have, and I can take questions.
Maybe I have a question myself. Oh, okay, go ahead.
Thank you. Thank you for the presentation. I basically have two big questions. The first question is how fast is the AI solver?
Yeah, so we tested our method with that like double integrator method at our Horizon like the 5, and on an M1 Mac, I think it executed the solve in 0.025 seconds. Yeah.
Is it only for 2 agents?
3, yeah.
3 agents.
Mhm.
Do you try increasing the number of agents? This is actually my second question.
Yeah, we haven't, but it would really be interesting to see how fast it can be with like several agents.
Yeah.
Another question, how do you train the trajectory prediction model? Is it also included multi-agent dynamics? Expert itself?
Yeah, so the neural network takes the input of the full joint state of all of the agents and predicts a trajectory forward of the opponents. So it since the data is just like bagged trajectory information, it just sort of tries to mimic that in an imitation learning fashion. Yeah.
But the expert policy controls all agents, right? So in theory, even the offline data contains these game-theoretic interactions, and you could utilize them to train a model offline without having the online interactions to solve the does that make sense? I'm just asking like what the expert policy is.
Oh, in the test case we did.
No, yeah, in the test case, like how do you train your diagram?
So we don't use like any trained model in the data collection phase. We just use the AL game solver, and we define like an objective where we have like a final goal state and just have everyone like try to meet that. Yeah. Mm-hmm.
Yeah, final question. So the neural network is directly predicting the states, the joint states.
Yeah. Mm-hmm.
Have you thought about instead of predicting directly the states, predicting something like a control input to model and then get the states from the model?
Yeah, I think that could also be an interesting approach to take. I think then you might need a really good dynamics model of the other agents in your system. But yeah, it could be an interesting approach to take. Yeah.
What are the inputs to the diagram? Like not using reading, but use the training model. What input we use? Because while training the model, we need to specific cost function. So the diagram is trained only for a specific cost function. So shouldn't the diagram be conditioned on the cost function?
So the trajectory predictor just tries to like minimize like the difference between like it's just imitation learning on the bagged trajectory data.
So the algorithm returns a actual delivery for the state, and so that there exists sort of a local optimal, but have you considered the use of it, like if it's only local, and what if there are multiple?
Yeah, that's definitely a really interesting question. I'm not entirely sure. I think it's also unclear because we're trying to like approximate the underlying ground truth objective with this tracking cost, and whether or not that's like always going to be representative of the underlying objective is, yeah, not entirely sure. Mm-hmm.
All right, thank you. We're going to move on to the next presentation. Right, so the next talk will be by Shaik, and the topic is cooperation dynamics in multi-agent systems, exploring game-theoretic scenarios with mean field equilibria. Sabahat, can you try to share your screen? I think you're also muted.
Can you please confirm if you can see it? Okay. Good morning, everyone. I'm Sabahat Shaik. I'm from Woxin University. It is an absolute honor to present at this conference on behalf of my co-authors, Vaigarai Sati and Professor Jashwant. Our paper focuses on cooperation dynamics in multi-agent systems, where we explore game-theoretic scenarios with mean field equilibria. The motivation for this project comes from wanting to explore newer ways to induce cooperation in multi-agent system, as the need for cooperation is critical in real-time multi-agent systems, like those involving autonomous vehicles. In this regard, our work proposes some strategies and approaches to induce cooperation without losing the priority of individual rewards. So the agenda of our presentation is as follows. We will be exploring different strategies, approaches, which encourages cooperation in agents. It plays an important role in multi-agent systems and multi-agent reinforcement learning, where we try to optimize both individual rewards as well as group rewards. We then address challenges caused by scenarios where a number of agents increase indefinitely via mean field approximation. We also try to establish equilibrium solution and reward structures by employing mean field game theory. And a few insights are offered using multi-agent posthumous credit assignment trainer by Unity Technologies. So our implementations mainly focus on increasing cooperation between agents. In the iterated prisoner's dilemma, it's a scenario where two agents must choose between cooperating with each other or betraying each other. So the payoff matrix is as follows. T is the temptation payoff, R is the reward, S stands for sucker's payoff, and P stands for punishment. The temptation reward when one agent cooperates and the other defects is much more greater than the reward when both of the agents cooperate. So the condition where two rewards is greater than temptation and sucker's payoff should be met to ensure the nature of the game. This means that both agents must cooperate to get better group rewards rather than trying to maximize their own individual rewards. Here we propose a new strategy where two rewards are less than temptation payoff and sucker's payoff. This not only encourages the agents to take turns obtaining the maximum rewards, but it also does not sacrifice the group reward. The mathematical equations to achieve the same have been derived using a discount factor for future iterations. This is essentially a win shift, lose shift strategy as agents shift their roles regardless of the outcome. So next comes the mean field equilibria. It's a scenario of intersection with large population of agents waiting to cross. This scenario is formulated to study the application of game-theoretic strategies to evoke cooperation in multi-agent systems. Each agent has two choices, to wait or to cross. However, the dynamics are influenced by number of agents who choose to move and the number of agents allowed to cross. Here, cooperation and defection is not an individual choice, but it is like a group outcome. The primary objective here is to develop a reward and equilibrium system. We implement an action space A in binary form where 0 stands for moving, stands for waiting, and 1 stands for moving. If the number of agents who choose to move are less than the threshold, then agents receive a good reward no matter the choice. If the threshold is less than the number of agents who choose to move, then the agents get least reward in both the cases. The equation to capture the evolution of mean field distribution is derived. The Bellman optimality equation is also derived, which represents the optimal strategy for a rational agent in a population where each agent's behavior influences and is influenced. Next, we get to posthumous credit assignment. It was originally developed with an intention to let agents know when the group has benefited from their actions. But we have noticed that after a period of time, the agent's role becomes static and the dynamism in their decisions reduces. So in context of mean field scenario, if the same J agents choose to move and the same N minus J agents would wait, by interchanging these roles of the agents dynamically, we can ensure that agent which chooses to move in this iteration would wait in the next iteration. Traditionally, again, in iterated prisoner's dilemma, this can be implemented using memory one strategy. So the memory one strategy is where the agents know their actions in previous iterations and modify their strategy accordingly. As the number of players keep increasing, the number of prior iterations can also be increased. The algorithm which details the implementation of our results is as given. So we have maximum number of laps, and we always start from lap 1. So at an intersection, when the agents move or wait, the rewards are calculated using the payoff matrix and our proposed uh, reward system 2R is less than temptation plus success payoff. So after each lap, the agent's memory gets updated with the choices that they made in previous lap. And then they adjust their strategy based on this memory. So if the agent chooses to cooperate and wait in this lap, then it defects and moves in the next lap. And it keeps going on until the number of laps have ended. So we evaluated the performance of our multi-agent posthumous credit assignment using a proposed modification, which encouraged dynamic role shifting and cooperation in 2 different scenarios. So the first one is a simple environment where the agent is supposed to go around the track, but only one of the agent is permitted to move. So using a proposed payoff reward where 2R is less than T plus S, and with the additional implementation of memory strategy, the agent takes turns while waiting while other agent moves in the current iteration. Since this is a very simple scenario, it did not need much iterations. So for next is dungeon escape. So the aim of this is for the agents present in the room to kill the dragon by sacrificing one of them. In this particular example, we have 3 agents and 1 dragon. So from the original training, it was observed that over a time, one of the agents gets sacrificed more often while the other agents escape. So in this, we established a memory strategy to dynamically facilitate role shifting. And if the agent has been sacrificed in at least the past 2 iterations, then the agent must escape in this iteration. This encourages them to not only maximize individual rewards, but also maximize their group rewards by taking turns, sacrificing one others. And in conclusion, the paper proposes how different strategies could be used to improve reward policies using a mean field game perspective. Though we did obtain considerable success with the multi-agent post-credit assignment, the complexity of this increases with the number of agents because it requires extensive iterations. So one potential solution for this which can be explored in future is stochastic decision making and probabilistic role switching. One of the realistic applications for this could be application of game-theoretic scenarios in ADAS and to analyze its impact of the driver's behavior in such scenarios. So that is all for now. Our paper link and also our project GitHub link is linked here. So if you have any questions, I could take them.
Oh, it was muted this whole time. Another hand for Sabahat.
Okay.
Next, we'll have a talk from Ehsan Hashemi. The title is Interaction Aware Merging in Mixed Traffic with Integrated Game-Theoretic Predictive Control and Inverse Differential Game.
I'm here to present our recent group research works on the interaction of merging mixed traffic using the integrated game-theoretic predictive control. And I'm presenting my students' works. This is a part of his master's thesis in my group. For autonomous driving, as you may have heard from early this morning, we are mostly facing for merging scenario the frozen robot situation, which means due to unseen dynamic situation in the environment, the robot is not able to decide about the next steps, specifically for the motion planning, and it stays within a specific velocity or within a specific states. It does not necessarily mean that the robot stops, but the thing is, robot may also move or the vehicle may also move, but it does not provide any steering to change the states. So the solution is including the interaction between the autonomous driving system and a human-driven vehicle in the mixed traffic scenarios. And for the main problem of the existing structures or existing sequential structures is the separation between the motion planning and the low-level control. So in this research, we were investigating the feasibility of the differential games with some integrated unknown input observer for estimating some parameters with proof of stability and the convergence of aerodynamics, and also using some LSTM methods to estimate at least the initial or nominal values of the parameters. As you can see in this picture, the existing methods mostly due to the separation between the trajectory planning and the low-level controller. They consider the objects or even the human-driven vehicle as an obstacle. They would also be able to estimate the states of the vehicle, dynamical states of the vehicle, but the interaction is missing. So for the last 6-7 years, there is a huge shift in this community to include the interaction between the human driver and also the autonomous vehicle. And it was also our main motivation. All right. This is the general structure or the pictorial representation of the problem that we have. We have a human driver vehicle that with a human that perceive the environment, visual perception, and it has some prediction over the states, dynamical states of the other vehicles. We have the controller in the automated driving system that has the objective function estimation. Why? Because we need to have some level of estimation, at least nominal values of the objective function of the human, because we do not have any communication between the vehicle, and also motion planning and control. And we also have some sensory information. It's multimodal sensory information. And when we move on towards the end of this presentation, I'm going to tell you what we did. We are using multimodality of the sensing, including the LiDAR and camera, to do the clustering, to do the state estimation, and then use that estimated state within this whole structure. Therefore, we have considered the bounded errors and the estimation errors at each level of this prediction for the whole structure. Going back to the differential game, we are assuming Nash equilibrium, and as you all know about this from early this morning, we all heard about this Nash equilibrium and the differential game. And the dynamical model that we are using for this system is a nonlinear dynamics, which means we are including the nonlinearity of the system, of the vehicle dynamics, and also nonlinearity of the tire forces. These are two main differences with the existing method that may consider vehicle as a point mass or may consider the vehicle kinematic model, but we are using or considering the high fidelity model of the vehicle. And we also have two cost functions, as you can see, JH and JR. We as the automated driving system, we know our cost function, but for the human, we don't know. But moving forward in the 3 slides from now, I'm going to describe how we estimate the human cost function or major parameters of the human cost function. Why we need a vehicle dynamical model? First of all, most of the emerging scenarios in the highway are high speed. And when you're driving in the 60 or 70 kph and the smallest steering angle up to 5 degrees at the tire level leads to the saturation of the tire, or you most probably work around the saturation of the tire in terms of lateral tire forces. The slip angles are around 6 to 7 degrees. Even on the dry surfaces, you're very close to the saturation. So considering the point mass of the vehicle is a very good assumption at the beginning for considering the interaction, but when it comes to the reality and the high fidelity simulation that we are addressing, considering the vehicle dynamics and also nonlinear tire forces is a must for our method. So the high speed maneuvers and the slip condition leads us to using the vehicle dynamical model. We consider both nonlinear vehicle dynamic model and also nonlinear tire forces, both for the human-driven vehicle and also the automated driving system. In terms of the states, we have an augmented states. We stack all the states together, states of the longitudinal distance between two vehicles, the lateral position of each vehicle with respect to the center lane or the center lane of the road, which is our desired value, and also the heading angle of the vehicle, the speed of the vehicle, and most importantly, the last 4 states are again contributing a lot in terms of maintaining the stability of the vehicle, lateral velocity and the yaw rate of the vehicle, both for the human-driven vehicle or the automated driving system. Because your optimization problem or the natural equilibrium may provide some solutions for the control action, but those solutions might not be feasible in terms of physical actuation on the vehicle. It may request 25 degrees, 30 degrees on the steering angle on the tires, even if your optimization problem is constrained. But that leads to instability of the vehicle. We have seen that a lot, both in our high fidelity simulators and also initial experiments that we had for the last 2 or 3 months. And the control inputs are accelerometer, acceleration, which are the gas pedal or the brake pedal, and also the steering of both human-driven vehicle and autonomous vehicle. I'm going to just jump into the cost function that we have here and what is the differences between this one and the kinematic model. The cost function that we have here, as you can see, we are including the desired speed and also the lateral position, which are, I mean, conventional. Many other literature are also considering these, but we also consider that term Vy, which includes the lateral stability of the vehicle, like that parameter theta3, and also the proximity of the two vehicles with respect to each other, considering the geometry of the road or geofencing or the geometrical constraints of the road, and also the steering angle. Therefore, this cost function is considering the geometrical constraints as well as the stability of the vehicle dynamical stability to reduce the lateral speed. Minimizing that Vy is a must for maintaining the stability of the vehicle. That Vy should be constrained. We cannot have 2 meters per second or 3 meters per second for the lateral velocity, because the vehicle may lose the stability and the trajectory moves towards the bifurcation in terms of the dynamical model of the vehicle. Again, in terms of the geometrical constraints, the vicinity of the two vehicles are simply modeled by elliptic representation. And now we have a whole problem formulation in terms of what are the control input to the system, what are the states that we are able to measure, and what is the interconnection between these two controls. But main problem is estimating the objective function of the human. How we are able to do so. As I mentioned at the beginning, we are using LiDAR, camera, and radar. We are using a side LiDAR, 16-line LiDAR, and also a stereo camera in front of the vehicle, and also side radar. We do the point cloud clustering, and also we do the image processing and the depth estimation to estimate the position of the vehicle, relative position of the vehicle with respect to us, and also the heading angle of the vehicle with respect to us. We are also able to identify or classify the type of the vehicle, the truck, sedan, or the tractor trailer. So all of these processes have been done in between 20 to 30 milliseconds in terms of the clustering and the state estimation. Therefore, using the LiDAR and the radar, we would be able to estimate the relative distance and the relative heading of the vehicle beside us. We do not need to use the GNSS with RTK solution. We just use onboard sensory measurement, proprioceptive measurement sensors. And this is the J is the cost function of the human, but the challenge is estimating these parameters. We not only need to estimate the theta parameters, but also the desired value of the Vx, which is the longitudinal velocity, because we need to regulate that, and also the lateral position. The way that we do is using a basis function approach that has been used again in the community for the last 7-8 years. And a new method was also proposed by some researchers at the Karlsruhe Institute of Technology in Germany, that they are using the separated base function and also the theta, that they were doing similar things, but they didn't consider again the stability of the vehicle, which is the element that has been added to this research, and also the interaction between the vehicles. Based on that basis function, we all know that each player aims to minimize the basis function, specifically the human. Phi of h, we need to minimize this, which minimizes the whole objective function of the human driver vehicle. For estimating of theta h, we use LSTM at this stage. And how we did so, we used 6 different users in each of them in 5 different scenarios. None of them has any idea about the objective function of the vehicle or the characteristics of the road. And we use LSTM to estimate the parameters of the model, parameters of theta h, which are required to be multiplied by the base function. After that, therefore it's more of an inverse differential game. We use LSTM to solve this and obtain the theta h within that block of the inverse differential game, and then we're going to use theta h for the motion planning and control. But one of the main challenges here is what is the control input for the human? Because as you all know, for this differential game structure, we need to know the control input of the other player as well. But we don't know that delta H is not known for us. Some research are focused on the estimation, V2V communication to obtain the delta H, but we are using an unknown input observer here to estimate the delta H. The way that we do is we use the relative acceleration, relative lateral acceleration, and also the yaw rate within a stable unknown input observer with proved stability and also proper convergence rate of the estimation error to estimate the unknown input, which is the delta H. And at the end, I'm going to refer to the paper if you're interested to see the proof and how we are estimating that. The whole system is satisfying the strong detectability condition for an unknown input observer, and we are able to estimate the delta H with some variances. The estimation error accuracy was between 10 to 12%, even on the experimental setup that we have. So technically, we estimate delta H using an unknown input observer, and then put it into the motion planning and control, which is game-theoretic MPC. As you all know, the closed loop Nash equilibrium is not really tractable. We may suffer from computational complexity because we need to solve this problem less than 30 milliseconds. Open loop Nash equilibrium might also suffer from inaccuracies in the high speed. Therefore, we combine the open loop Nash equilibrium with the MPC over prediction horizon. Over between 8 to 10 of the samples of the prediction horizon, and our sampling time is 20 milliseconds. Therefore, within 200 milliseconds, we have this MPC connected to the open loop Nash equilibrium to solve this whole game-theoretic MPC problem. And again, we stack the gradient. As you can see on the bottom, we stack the gradient of the human and also the gradient of the automated driving system and also the dynamical constraints to solve this minimization problem for the Nash equilibrium. And at the end, for the differential game plant, in our motion planning and control, as I mentioned, we are using nonlinear vehicle model and the nonlinear tire forces. And we were able to, one of the contribution in this work is we were able to separate the control input from the states in the nonlinear dynamical model. X dot was written in the form of fx plus g multiplied by u, including the slip. And that helps us a lot in terms of proving the stability and also the computational efficiency. That was on the green box, the GTMPC. But what about the plant, the real plant? We do not have this two vehicles right now to do the testing, but we use the high fidelity simulator car sim to do so. Both human-driven vehicle and the autonomous driving system has been modeled in car sim. With high fidelity that includes the road surface friction, a slippery condition, and also the load transfer. And this is our setup. We have that white vehicle that you can see on the right side of the image is the human driver, and the red one is the autonomous driving system that wants to merge it. We integrated the Unreal Engine from the MATLAB automated driving toolbox, connecting that to the car sim. Therefore, the plant, the differential equation of the dynamical system has been solved by car sim, but the visualization has been done by MATLAB, by Unreal Engine in the MATLAB automated driving toolbox. Our drivers are sitting behind this simulator. Between 6 to 8 different drivers has been tested in 6 different scenarios on the dry and the slippery surfaces conditions. And then we try to not only estimate the parameters, theta h from the LSTM for different drivers, and also to see the feasibility of the differential game for this problem. And this is the video that I can show for one of the scenarios. This is an interesting scenario that the human driver, which is on the left side, is not cooperative. It does not reduce the speed. And I'm going to show in the results later on in the next slide that some of the baselines that they do not consider the interaction, the automated driving system is waiting and waiting to reduce that the human driver reduce the speed and then merging, and then the geometrical constraints are not satisfied. Sometimes they may deal with the frozen robot problem. Sometimes they pass the geometrical constraints. But with this interaction hour scenario, we were able to, after 4, I guess, or 5 sample time, the automated driving system was able to detect that the human driver is not cooperative and increases the speed to do the merging. And our objective for merging is, as you know, merging in front of the vehicle. Because the perception of the automated driving system might not be very complete and comprehensive to know what's happening behind the human driving system. So our main objective was merging in front of the human driver vehicle. As you can see on the middle plot and on the right plot, the middle plot shows our method. And on the right plot, you can see, on the right column, you can see the baseline. For the baseline, the automated driving system, which is the blue one, was waiting for the human driver vehicle to reduce the speed, and it didn't happen to reduce the speed significantly. But for our proposed method, the automated driving system at the beginning, after 4 or 5 samples, it realizes that the human is not cooperative and increases the speed to do the measuring safely. In terms of conclusions and future work, for conclusions, we are still exploring this GT modeling, game-theoretic based modeling with the MPC for highway measuring and also the roundabout problem. And so far, in terms of time efficiency and computational efficiency, we were able to do that in less than 30 milliseconds, and also with the onboard sensor measurements. But one of the challenges that we have is on the various road surface friction conditions on the slippery surfaces. Although we are using the nonlinear vehicle dynamical model, but the stochasticity of the road surface friction and the whole dynamical system for those maneuvers close to the saturation is a big challenge. We are right now focusing on that. And we are also focusing on bringing transferability of this algorithm on one of our vehicles, our automated driving system, to see how it performs in the real practice. That's all. Thank you.
Audience. Thank you. Oh, there's a question.
So my question is related to the objective function. And I understand these are like the basis functions. And so there, anytime you're factoring a single hypothesis, but have you considered maybe how it would be to say multiple hypotheses, multiple understand something? And so you got multiple hypotheses instead of only one.
Yes.
So how
we have not investigated that. I mean, from the multiple hypothesis perspective, but the thing is, we investigated the correct estimated state or the correct parameter or the accuracy of the parameter estimation on various excitation level on the system, which means different steering, because the steering is the control input to the system, and also different longitudinal acceleration or longitudinal brake. But for the various hypotheses, no, we have not tested that. But that might be a good approach to see the effect of, because this theta h then would be propagated throughout the whole system. If it's not accurate, it will also affect the accuracy of the GTMPC. But no, we have not considered that one. We considered different excitation level, because the problem was the state estimation, and we were focusing on variation of the excitation to have a better estimation.
Any other questions? Thank you very much.
Thank you.
And then next we'll have Guan from Georgia Tech, and the talk title is Zero-Sum Games for Large Population Heterogeneous Teams, a reachability-based analysis under mean field sharing. And I will make you a co-host now.
Yeah, thank you. Can you guys hear me?
Yep.
Great. Let me share my screen. Second.
Yep.
Okay, I guess everyone can see it, right?
Yeah.
Great. Let me get my laser pointer out. Yeah. So thanks a lot. So I'm Scott Guan from Georgia Tech. So today I want to present our recent work on zero-sum games between heterogeneous teams, a reachability-based analysis under mean field sharing. So in the past few years, we have already seen a lot of zero-sum game between two agents. For example, we have the chess, the go, or we may have some kind of more general zero-sum scenario, for example, a rock, paper, scissors game. But I think there's a motivation that we want to extend this two-agent competitive setting to a more like a team against team scenario. Maybe we want to consider a StarCraft scenario where we have the red Terran attacking the blue Terran, or maybe we just consider some kind of military engagement. So those scenarios are obviously not agent against agent, but more of agents, a team of agents against team of agents scenario. So like I said, in this work, we want to study this team against team scenario, which is a generalization of the zero-sum game between two agents. And then we generalize that to two competing teams. And the agents within each team will receive the same reward. And naturally, this is a mixed collaborative and competitive setting. Namely, at the team level, agents need to compete against each other, but within each team, agents need to collaborate so that they can maximize their own team reward. So this scenario may also have some kind of non-classical information structure. So agents may have common and private information. For example, if we consider some kind of battlefield scenario, the common information may just be the weather, where both teams can observe, and then private information can be your intention or the location or allocation of your resources. So the naive approach for these kind of scenario is basically we can just create a centralized super agent and then just stack everyone's state and actions into a single gigantic vector and then solve in this joint state and action spaces. But the issue here is that this complexity scales exponentially with the number of agents. This kind of naive approach may not be able to accommodate the underlying information structure, for example, the common and private part of the information. So that's why we want to study a very specific class of this team against team scenario, namely the mean field type of interaction. So here are some assumptions that we'll make. So we will consider a zero-sum simultaneous move game between two teams of agents. We assume that each team consists of different subpopulations. So for example, in this battlefield scenario, we have two teams, the blue team and the red team. The blue team has two types. So it has the dark blue type and the cyan type. But one of the key assumptions that we make here is that even though teams may have arbitrary finite number of subpopulations, agents in each subpopulation are homogeneous. Basically, they have the same dynamics, same action space and state space. And then we study a finite horizon problem. We assume that we have finite state and action spaces. Now is the most important part of this this work or the assumption. We assume some kind of weak coupling between agents in terms of their dynamics and also the reward. So by saying weak coupling, I mean that each individual agent's movement or their transition is influenced by the whole population in this game, instead of by a very specific agent or a very specific subset of agents. So if we do have this weak coupling, we can theoretically show that now, instead of using the joint states of the agents, which keep track of each individual agent's whereabouts, we can aggregate this information into something called a mean field, or basically the state distribution of the agents. So in this case, we only need to keep track of the state distribution of the dark blue agents, the cyan agents, and the red agents. And then those information is enough for us to predict how the system will evolve in the future. So we can actually show this theoretically. And then just notation wise, we just call these the team state and also the team distribution or team mean fields. Next, I want to quickly talk about the information structure that we're looking at. So we consider something called a mean field sharing information structure. So what happened here is that we assume that each individual agent can observe the mean field or the state distributions of both teams, and then it will also observe its own state. And then based on these information, it will select its action. So going back to the battlefield scenario, for the blue agent, it will observe its own location and then a state distribution of the two types of blue agents as well as the red agent. And then based on that, it will select its action. As you can see here, we have the common plus local information structure. So the common information is basically the mean fields of both teams. And then the local information is basically that individual agent's state. So to make this problem tractable, we will restrict our attention to identical team strategies. So by saying an identical team strategy, I mean that all blue agents of the same type will apply the same strategy. Similarly for the red agent. We will justify this restriction shortly. The optimization objective here is based on the discounted cumulative reward. And then we let the red team to minimize and then the blue team to maximize in this scenario. So because of the time limit, I'm just going to quickly go over how we solve this almost intractable problem under this very specific dynamic structure. So we start with an n-agent system. That's basically the original problem. We run something called a mean field approximation. Basically, we use an infinite population system to approximate this finite population system. So what this infinite population system buys us is that now the mean field or the empirical distribution becomes deterministic. And then that's very handy when we design the algorithm. And then at the infinite population limit, we will introduce two fictitious coordinators, one for each team. And then that will basically reduce this team against team scenario into a zero-sum game between the two coordinators. So the key feature here is that we will assume that this fictitious coordinator will assign some kind of identical strategy for each of the subpopulations. So this significantly reduces the computational complexity of this problem. And then for the zero-sum game, we will find the max-min coordination strategy, and then we'll translate it back to the original n-agent system, and then we will show that this policy that we obtained under this framework is still epsilon suboptimal. So now this is basically the main results for the performance guarantee. So suppose we obtain some kind of policy under the proposed framework, under the assumption that we are at the infinite population limit and then all agents applying identical strategies. This will still be an epsilon optimal blue team strategy in the original finite population game. So now let me clarify this or elaborate a little bit more. So what I mean by epsilon optimal is that suppose I apply this policy in the finite population game, in the original game, and then this policy is assuming that both me, all my agents, and my opponent's agents are applying identical team strategy. Now, I allow the red team, basically my opponent team, use some kind of non-identical policy to exploit my identical policy. Then obviously my performance would be great. But this degradation is basically bounded by this order of 1 over square root of n, comparing to the true optimal solution that I could have achieved by using non-identical strategy from the very beginning. So this has a significant implication. It basically says that if you just restrict your attention to identical team strategies, that will significantly reduce the complexity of the problem, but at the same time, you only lose a small amount of performance. And then the small amount of performance decreases when your team size goes to infinity. All right, so now I'll give a quick numerical example. So here is a very simple defense scenario on a two-node graph. So we have the blue team as the defending team trying to minimize the number of red agents on node 2. And then the blue team is a heterogeneous team, so it has two different types. So you have the dark blue type and also the cyan type. So this blue type of the blue agents is very effective in fanning off the red agents, but at the same time, it's less mobile. So basically, it can only move from node 2 to node 1, and then once it's on node 1, there's no way it can come back. The cyan agent, on the other hand, is less effective in fanning off the red agents, but they are more mobile, so they can move freely on node 1 and node 2. The red team, the attacker team, is homogeneous, and then they can always move from node 1 to node 2. So what we observe here is that we have different behaviors for the blue team when we have different composition of these two subpopulations. So in the first scenario, if we have a small amount of dark blue agents, but the majority of the blue teams consists of the cyan agents, then what we can see is that the cyan agents will move from node 2 to node 1 to basically defer the red agents transitioning from node 1 to node 2. And then in the end, they will all go to node 2 to basically boost the final defense at the terminal time step. What we can see is that the dark blue agents will actually split part of its population to node 1 to help with that defense. Is basically sacrifice 0 to get a little bit more performance in the end. However, if we have the majority of the blue team as the dark blue agents, then the dark blue agents basically serve as the major force in this defense scenario. Then they just cannot risk to move to node 1 and then leave node 2 undefended. So they always stayed on node 1. And then because of node 1 is basically ignored or given up by the majority of the blue team, the cyan agents will also mimic that kind of behavior and then mostly just stay on node 2 in this scenario. So I think that's quite interesting. At the same time, we choose this very simple scenario because we can actually compute the true optimal solution for the final population game, and then we compare that with what we have obtained running the coordinator type of approach, and then indeed we can verify this performance degradation is bounded by this 1 over square root of n bound. So now I want to quickly conclude. So in this zero-sum mean field team game setup, we showed that by restricting our attention to identical team strategy, it will only lead to a small performance loss. And then the performance loss diminishes as the number of agents approaches infinity. So this has a implication for different multi-agent algorithm. Basically, you can only train a single actor critique network for each team, and then you will still get good enough performance. So for some future work, we're looking at the LQG setup of the zero-sum mean field team game. And then we also want to investigate scenarios when only local information on the mean field is available. And we may also want to perform some kind of estimation on the opponent's team's mean field instead of directly assuming that we have access to that piece of information. This is basically my presentation, and thank you for your time. And I'm ready for questions.
Questions from the audience? So I have a question on for a more realistic, let's say, simulation. How are there any insights on how we would distill it basically into kind of a state machine type scenario? Like, for example, you said StarCraft. I imagine it's really hard to put it into this similar state where you'll have the where you can actually discretize the state where all the agents are.
Yeah, I agree with you. I think a lot of the game theoretical approach, at least that you have some kind of performance guarantee or Nash equilibrium guarantee, is always on the highest level of decision making, and then you may have some kind of low level controller to follow the trajectory, right? So that's the way I look at this kind of scenario. So maybe we will discretize this the StarCraft environment to some extent, but at a coarser resolution, and then provide some kind of like high level command to each individual agent, and then the low level execution will probably just be done by some other kind of controller or something like that. But yeah, I do agree with you. This weak coupling assumption is relatively strong, but I think if you think about the game at a coarser resolution, I think to some extent it makes sense, but not at the finest resolution. I hope that answered the question.
Yeah, thank you. Any other questions? All right, thank you very much. And we'll move on to our, there's a question from the chat. Would it be possible to consider a generalization of this information structure?
Yeah, I'm not 100% sure what kind of generalization you're considering, but I mean, a part of the future work that we want to consider is this local information on the mean field is basically like a partial observation of the aggregated state to some extent. Maybe that can be a generalization of the information structure, but in order to get to this perfect information game kind of scenario, I think this is the least amount of information that we do require. So I don't think we can decrease the information any further.
All right, thank you.
Thank you.
And we'll have our last talk from Kalani Fei. The title is Towards Risk-Aware Racing Agents, Learning Adaptive Policies in Competitive Racing Games. And I think you already have, yep.
Cool. Just double checking to make sure everyone can hear me okay?
Yep.
Okay, perfect. So hello, everyone. My name is Kalani Fei. I'm an undergraduate at Pomona College. I'm studying mathematics, and this is work, very, very preliminary work with my academic advisor, Professor Victor Shia at Harvey Mudd College. So sort of the key motivation of this work is a lot of work has sort of gone over how do we create risk and sort of safety aware policies while still ensuring that we meet our goal. And a lot of these goals can be whether human robot interaction or autonomous driving, and sort of trying to figure out, okay, like how do we figure out like a good way for a robot to preemptively plan for and take into account like how safe is a certain action before it's actually taken. And so sort of in a new vein of work, this has been recently explored by taking in economics and sort of risk-aware policies from economics and stock markets in order to sort of shift these into robotics and figure out like, okay, like how can we actually ensure this in the real world, and do these sort of risk-aware policies actually make our robots safer? So sort of as a brief background into risk awareness, so one of the first initial works in robotics sort of risk awareness was through Majumdar et al. In 2020, and this looked at sort of how are variable risk metrics defined and what makes a risk metric better than other risk metrics. And sort of going through a bunch of axiomatic properties, such as translation and variance, they found that critical value at risk and variable at risk were found to be the best forms of risk for robotics, due to axiomatic properties that they exude, which can help make them more safe. And so initial applications since then have been explored into exploring like how can we actually improve risk into our risk-aware motion planners? How can we use and create risk-aware linear quadratic regulators, and looking at sort of a wide variety of intersection with this work, including lane merging in Wang et al. In 2023. And so lastly, looking at the background in this intersection of game-theoretic motion planning, multi-agent reinforcement learning, and reinforcement learning for risk awareness, several different works have begun to explore autonomous driving and the applications of using risk awareness. These planners include exploring game-theoretic approaches, multi-agent reinforcement learning, and risk-aware controllers. However, a lot of these prior approaches often assume either cooperation with other agents, single agent scenarios, or have to make a lot of strong assumptions about observability. And so this whole vein of work of risk awareness and autonomous driving remains pretty open as a question and ongoing. So the goal of this project is really to sort of break that down a little bit more and to explore, can we actually use risk awareness to help agents in in competitive and non-cooperative games to reliably still win while having an awareness of safety costs? Secondly, I hope to, throughout the continuation of this project, to see if collision actually decreases through using risk-aware models, test if through common or prediction-inspired sort of frameworks can help give better predictions of risk under changing behavior. And lastly, through this all, I really hope to see if policies are adaptive under dynamic strategies of human opponents, including variable aggression models or variable risk levels. So sort of for the setup of this, I've looked at extending Trackmania. I use this because it's a single player deterministic racing game. So if you do the same input on your controller, you'll get the same output every time. And I want to be able to repeat sort of games. And so I extended it to be 2-player by adding in collision checking and ending the race if there is a collision. You put in a custom LiDAR measurement that was from an open source framework, so we can get LiDAR observations and also camera observations if you choose to, and created a custom racetrack that was wide enough so we could run with 2 players and read in state information of both players, state being position and velocity. So in order to try and solve this problem of, okay, can we create a racer that is competitive, but also is able to be risk aware? I created sort of these it's a reinforcement learning framework where the human policy takes into account past actions, encodes them to predict and give an output of what they think the opponent's risk is and the predicted state, and then feeds this to a base policy, which outputs the next action. Likewise, for the robot, it does the same thing, but except for it's predicting for the human what the expected risk is, for the encoder, expected adaptation, which is change in risk, and expected predicted next state. This is then fed into the base policy, which gets fed into finally like a zeta encoder, which says, okay, like how wrong were we and how much should we adapt our given past prediction for the next step. And this acts as a correction step in case one of the robots, if you have a beginner or you have somebody who's like rather new and then learns that they should be a lot more aggressive, how can we adapt and take that into account for future states? So for initial rewards, I frame it as the same for both the human and the robot for the reward, except for the robot has an additional information probing policy, which is the I function at the end here. I say that the initial baseline reward is how far you are along the track or the closest center line point relative to your other opponent. I say that there's a safety cost, which is based off of the current location of both players, the speed and the relative heading. And I scale this by the critical value at risk level. So how risky was the action that you actually performed? And then finally add an information gain, which is to help, given your expected output where you thought the player was going to go, how correct were you in order to help the robot to learn actually where is the human player going to go. So for defining risk awareness, I define it as risk is defined because I'm using critical value at risk as this function. I define the probability as two overlapping sort of Gaussians, and I say that the collision risk is 1 minus or the overlapping point. And I define it as purely based off of distance and the covariance of which based off of velocity. And so for a very, very initial work, I went ahead and I collected it. Originally, it was for 50 different players in order to train my encoder of figuring out where is the human player going to go, what is sort of the risk level that players are exhibiting, and also trying to check if risk actually does matter in these sort of two-player racing games. So I ran this with using the state information reader that I created, and we found that risk does matter. And so in cases where an opponent there was a big difference in risk levels, one opponent tended to win much more often than the other, typically the one with a higher aggression, but not always. And then in cases where there was a similar risk level, then typically both agents had a very similar and close race. And so I've used this to try and train an initial encoder for predicting state and also getting started on training sort of the initial full model. However, that is still ongoing. And so I'll be finishing up testing the full policy. I do have a full policy that does train both of the agents, but the work is a little bit too preliminary on results to release yet. I have been deploying this, or I'm going to be deploying this against human opponents instead of the sort of trained and fake human model that we've created. Comparing this as well for setting convergence and making sure that it is actually converging to a policy that works across many different racetracks and many different human players, and also underneath different types of strategies, such as edging, blocking, and different sorts of competitive racing and varying risk strategies. Yeah, so that is the presentation, and I'm now open for questions. I can't hear you super well. If you come up to the microphone, if somebody can repeat it in the microphone, I think that will help.
I had a question about, can you hear me?
I can hear you, yes, thank you.
I had a question about what if your collision risk is multimodal? Is C-bar still good enough?
Yeah, so that's one of the axiomatic properties. I believe that it does work underneath multimodal distributions.
Thank you.
Any other questions? All right, thank you very much. I'll hand it over to Rahul to wrap this up.
Thank you. That was a good talk. Thank you. All right, so we'll just wrap up for the day here, and let me just in 2 minutes. So. Sorry, this is just a different computer, so. All right, so I just wanted to conclude with, just give me 1 second and then I'll. Yeah, so I think we'll that's okay. I think we can do away with, and we had enough slides today. So the day, was packed. I think we had a lot of exciting talks, and I also saw at peak we had about 72 people in the audience, so it was really well attended. With you can see that over here, and so I think overall this topic has many different people from many different communities have come together to talk about these issues, and bringing in dynamics obviously makes the problem much more complex. So as I mentioned before, we will also, this workshop is the theory complement to what is done in actual scale racing, and as part of the IROS competitions, we are hosting the F1 10th Autonomous Racing Grand Prix, and that will be from tomorrow for a practice day, and then Tuesday will be time trials with different teams. So many different teams have come from all over the world, and they all compete on this standard reference design, but they bring their own algorithms for perception, planning, control. And then on Wednesday, you will get to see head-to-head races. We'll also have this at ICRA and CPS Week and IROS again next year. So I hope you enjoy the actual races, and I hope this workshop also triggers some more collaborations across these community borders. Thank you so much.